Thank you so much, Tanya. Thank you, Stephanie, Friendly Text Base. Hello, friends and family. Hello, thanks for joining. Today we're going to talk about data. What is data? If you were to touch it and like hold it, what would you feel? Or if you were to smell data, what would it smell like? If you have stale data, does it get all soft and spongy and grow funny spots? Now I don't know what data smells like. But we're going to talk about how data has evolved, specifically like about what it physically is. So to begin, hi, I'm Jacob. Like Tanya mentioned, I manage a team of data analysts and data platform engineers, and I've been in the data field for about 10 years now. So on to today's topic. To the crowd, throw it out there. What do you think is the oldest documented example of data storage? Feel free to comment or unmute yourself real quick.
I don't know, but I like the vinyl DJ turntable. Is
Vinyl?
that spoiler?
Okay. All right, maybe. Anyone else? Vinyl, it's in the same galaxy. So, so the oldest example that I was able to find is this Ishango bone, which dates back to 19,000 BC from the Republic of Congo. They would inscribe things in this bone to keep track of numbers and like count things. Then a couple millennia later, on a different side of the planet, in the Incan Empire, they used this tool called the quipu. I think it was invented on a Wednesday, but it was essentially a way to store data. So if you were a tax collector and you wanted to know how much to charge people in taxes or how much someone paid last year, you might use a series of knots and strings to document what someone's taxes were last year. Or if you're a farmer and you want to know how many maize you planted last fall and how many you harvested in the spring, this would be a really excellent tool for capturing that data. On a different part of the world, they started using clay tablets. Again, it was a really good way to store data. It was hard to edit after it dried, but if you, for example, like had a barley harvest and you paid people to come and harvest your barley for you, you might want to keep track of how much you paid folks. This kind of manual, like putting something on a physical form and then using our brains to process data, has been the way humans have done data processing for millennia. Eventually, clay tablets evolved into papyrus, which then evolved into paper, which people to this day still use to capture data. This, you see some gardening records, but people would store all types of data on paper, including medical records. And then in the 1600s, someone decided to capture a lot of written data and do analysis on it. They attempted to predict life expectancy by taking notes about and capturing like deaths across Europe. This gentleman, John Gaunt, published a book. It's a real page turner. It's called Natural and Political Observations Mentioned in a Following Index and Made Upon the Bills of Mortality. Really exciting in the data space. Someone captured a lot of data, did some math on it, and predicted mortality rates. So folks were writing stuff down for a long time, but it was kind of getting difficult to process this data in the little processors between our ears. So folks decided to figure out a way to capture data and then let a machine process it. And the earliest form of machine-powered processing came from the textile industry. So if folks wanted to capture a text, like a design in textiles, they figured out a way to program that design and have the loom build it. So we're going to watch a quick minute video it's silent, but it's going to explain how this happened. Pretty wild, right? So you could see that like the absence or the existence of a hole in the piece of paper kind of told the loom which threads to lift up and which ones not to. So this was like in the early 1800s, and some folks in Europe kind of saw this and were like, "Whoa, let's take this beyond the textile industry. Let's just store data for all sorts of things." For medicine, again, was a really big industry that wanted to store data. And folks, someone invented this tool called the homeoscope. There are other folks who invented a thing called the analytical engine. I think his name was Charles Babbage. But they all kind of had the same gist. This tool the homeoscope was designed to see if we can store treatments for diseases. So you could imagine they had a pneumonia stack, and it was a little stick with pins sticking out of it, and they would run that stick along this perforated piece of paper to identify a match. So here on the left might be the piece of paper. The bottom row here each cell might indicate like a letter or a number. And we would punch holes in the paper to like signify like A is like this unique combination of cells, B is this unique combination of cells, etc. And then we'd get a stick and pins, and for pneumonia, if we knew someone, if you could treat pneumonia with leeches, you would make a leech stick, push the pins through so that it matched on the leech column, and you put it in your pneumonia stack. And now you knew that if someone ever came in with pneumonia, that was what you would do to figure out what to teach them. So this concept of like punching a hole in a piece of paper and then finding a match evolved into the punch card computer. So we're going to watch another video. It's going to be about a minute. This one is not silent, but we're going to explain quickly what punch card computers looked like.
Being punched onto a computer card.
Jacob, I think you have to unmute yourself in order for the audio to play.
Is also utilized to represent alphabetic characters. Here we see a typical portrait.
You missed all that really great audio. Essentially, they were saying that whole like numbers at the top were signified by certain combination of holes in the paper, and they're going to show you
coding form and a Fortran punched card. The Y, for example, is represented by holes punched in 2 different rows. It is not at all.
Were y'all able to hear that? Okay.
Yep,
Okay,
perfect.
cool.
The limitation of recording tools, yeah.
Okay, thanks.
Being punched onto a
So I'm going back to this GIF because it actually used the same concept. It punched holes in paper, and instead of having a stick with pins sticking out of it, we sent bolts of electricity across the paper. And if that electricity made it through a hole, then you knew that there was a hole there. It was a really, really crazy and exciting innovation. It was used for elections, voting, and just businesses all over the world started adopting this punch card computer. There was a computer card punch where you could type something and it would make the holes. And there was a punch card reader that can take the cards and read it. The unit of measurement, the speed at which one of these computers ran was cards per minute. And it was usually about 300 to 2,000 cards per minute. So now I want to do a brief interlude because things are about to get crazy. I had a great professor back in the day who used to say, computer science is the science of abstraction. So this is going to become relevant because the data is going to get to a point where we can't actually see it with we can't see the individual holes in the paper. So computers are just built on abstractions. Programs that you run are written with programming languages. Those programming languages sometimes compile into other programming languages, which then compile into something called assembly, which eventually gets compiled into ones and zeros, binary. And binary, ones and zeros are the last step from when software bridges the gap into hardware. So you could think of like ones and zeros, they kind of become, they enter into what are called transistors, which are essentially like a this way or that way gate for electricity. So like a 1 would tell the transistor, like, send electricity to the right. And a 0 would tell the transistor, send the electricity to the left. So that's how we process. That's how the computer processes things. And we also have abstractions for how we store things. So audio, images, video, and just regular data, it gets encoded through different types of encodings into ones and zeros. And then those ones and zeros get abstracted. They get turned into holes in paper, or magnets being polarized or not polarized, etc. So we're going to talk about magnets, cassette tapes. A lot of data storage happened on these magnetic tapes. And it was essentially a bunch of magnets on a tape and then a bunch of things to like keep that magnetic tape like stabilized. And the magnets were either positive or negatively charged. And any combination of positives and negatives would equate to a series of ones and zeros, which would then build back up into whatever it is you were trying to, whatever data you were trying to store. This same exact concept is used on hard disks. Hard disks are still used today. Many computers still use them. And they work like this. You have what are called these platters, which is the disk. But the disk is essentially just a bunch of circles with magnets. Each circle is made up of thousands, tens of thousands of magnets. And we have this little spindle here. And what this thing does is it just reads the magnets. It just reads if the magnet is positive or negatively charged. The way data storage works, you want to optimize where you store your data on these platters. So you could think if you have an image that has 1,000 pixels, those pixels might be, you would want to store all 1,000 pixels like right next to each other on the disk. That way, when the spindle is reading them, it only has to do a tiny little rotation to get all the data. Or if you have a song, for example, music, you don't want to store the first 20 seconds here and then the next 20 seconds over here. and then the third 20 seconds on a different disk, it'll be really hard for the computer, for the spindle to find the first 20 seconds and then seamlessly jump to the second. So what we do is we store the entire song in sequential order on the hard disk. This affects our decisions when we decide to use row-based databases versus columnar storage. So if you have a database where everything is stored in a row, it's like row-based storage, like MySQL or Postgres. Everything in your row will be stored next to each other. So you might have like first name, last name, date of birth, address for the first row, and then first name, last name, date of birth, address for the second row, and so on and so forth. But if you wanted to do a columnar data storage, like Redshift, that will actually store everything based on the column. That will be stored next to each other. So you would have first name, first name, first name, first name, first name, last name, last name, last name. So those would all be next to each other. And you can imagine that if you want to access, depending on how you want to access your data, that could tell you what type of, where your data should be stored relative to each other. If you store an index of a database, that will essentially take a column and then store everything in that index right next to each other with pointers to where to each record. Similarly, when you specify column type, so if you say that a column is going to be a varchar with 248 characters, that tells the database whenever you insert a record, save 248 characters worth of magnets in this gap right here. Because like even if you don't write there, like we want to make sure that that space is available. And lastly, the other way this kind of ties into our work is with deleting and updating things. So let's say you have a table with 1,000 records, and you delete the middle 900. So now your first 50 records are over here, and your second 50 records are all the way over here. It would be inefficient for the database to spin all the way around just to get these 100 records. So it has a garbage collection function where the database, without us knowing it, will say, oh, I see these 900 records worth of magnets are like not being used. Let's clear them, move these 50 right next to these 50, and now our database is all right next to each other again. Similarly with updating, if you want to change someone's last name in your database, it won't go right to that column and update it. It'll write it somewhere else in case it breaks along the way. And like you don't want to lose, like in case you're doing a serious transaction, it'll write somewhere else and it'll mark that column as like stale, no longer used. And then eventually, if you run a vacuum or a garbage collection process, it'll identify all the stale bits and then move the real bits of data right back to where they belong. So this data storage is also how floppy disks work. This technology is essentially what a floppy disk is. It's just a magnet that's encased in a plastic like protection thing. This was a really innovative and exciting development in the data storage space because you could imagine it's a lot faster than 2,000 cards per minute. It's a lot safer. You don't have to carry around a huge box of cards. You don't have to make sure your cards are in the right order. You don't have to worry about like if the holes are punched properly. But what you do have to worry about is like the magnets kind of not working or like dying out or losing their charge. So that brings us to the solid state drive. This is awesome. This was like a crazy development. It's fast, it's durable, and it is going to revolutionize the way we store and process data. It's also sometimes referred to as flash memory. It got that name because the early adopters or inventors felt like the deletion process reminded them of the flash of a camera. And I'll tell you about the deletion process a little later. So we're going to dig in to to how these solid state drives work. And we're going to talk about the smallest unit of work, the smallest entity within these solid state drives. They're called charge trap flashes or charge trap flash cells. So we're going to watch like a minute video.
This is the basic unit of a computer's long-term memory storage, and it's called charge trap flash memory. So, how does it work? Well, in each cell, we can store information by placing different levels of electrons onto a charge trap, which is the key component inside the memory cell. Older technology could only store 2 different levels of electrons. A lot of electrons or very few electrons, which were used to store a single bit as a 1 or 0. However, engineers have been developing more finely tuned capabilities for trapping and measuring different amounts of electrons or charges onto the charge trap. Most memory cells in 2020 can hold 8 different levels, but newer technology can have 16 different levels of electrons. This means that a single cell, instead of holding only 1 bit as a lot of electrons or no electrons, can now hold 3 or more bits.
So yeah, charge trap flashes. This is the smallest little thing inside our SSD drives, and our SSD drives have millions of them. And as the technology improves, you can see that they can store more and more bits within each cell. So just to take it back, we've gone from a bit being a hole in a piece of paper to now a bit being the absence or presence of a certain amount of electrons. And that's happened over the span of like 40 or 50 years. So solid state drives have a lot of these tiny little cells, and I'm going to show you now how they kind of all work together to provide us with data.
Composed of 10 charge trap flash cells layered one on top of another. When information is written to or read from a string, only one cell can be activated at any given time. And to do that, we use separate control gates attached to every layer in the string. It works like this. The bottom control gate first says, "Hey, you, charge trap 1, what's your electron charge level at?" Then the bottom cell sends that information through the center of the string up to the information highway at the top, which is technically called a bit line. Then the next control gate for the second layer asks for the charge level in the second cell, and so on up the string, each cell sending their information up to the highway or bit line. The same kind of sequence happens when charges are being added to a charge trap, which is how information is written to a memory cell. The main thing is that only one layer in the string is either written to or read from at any given time.
Just to highlight that one more time. Only one cell can be read from or written to at a time. So keep that in mind.
Let's move on in complexity. Next, we duplicate this string 32 times, and this gets us a page of strings. Let's review some terminology. This is a memory cell, and this is a string. And now here we have a page, and we're going to call this entire page of strings a row. When we duplicate the string, we also duplicate the bit line 32 times. However, rather than duplicate the control gates, we're going to have every cell in the same page share a common control gate. This makes it so that when information is written to or read from a row, an entire page composed of 32 adjacent cells, all in the same layer, are activated at the same time.
So this is kind of where that discussion we were having about magnets on a disk being next to each other kind of makes it easier for the computer to process your data. Same concept here. The computer wants to put relevant data next to each other along these control gates. So if you have a photo, your pixels might all be stored in these cells along the same control gate. That way you're only sending one beam of electricity instead of n beams of electricity to get your data. And then a couple more seconds.
Let's step up in complexity again. Next, we duplicate these rows 6 times until we get a block. But we're going to do it 12 times so we can see 2 blocks. Okay, so again, here we have a column, here's a row, and this is a layer. And now here's a cell, and here's a string. Next, we have a page. And finally, we have a block.
I thought that was just comically confusing, the way they added all these things. Like, let's just, don't forget. Yeah, so like I said earlier, storing sequential data, you want to put it on the same page, essentially. I mentioned a while back, like the flash of like charge trap flash or flash memory. That goes to the fact that you can't edit individual cells. And you can't delete individual cells. In fact, you can't delete data from individual pages or rows or strings. No, you can only delete data at the block level. So if you're storing data in a database and you want to edit, and like let's say it's name, birthday, first name, last name, birthday, address, etc. Someone changes their address, you can't tell the solid state drive to go find the row that has their address and change the electron count within those cells, because that is too small of a unit for the solid state drive to like clear out the electrons. So what it does is it'll write your update to a different block, and then you essentially have like your row here, and you'll have a stale address right next to it, and then their new address will be in a different block. And so the programmers behind these kind of abstracted away this process, because it'll run some sort of garbage collection process again, and it'll say, oh, I see you have some stale data here. Let me move these things to this cell. Let me just clear this block out completely so that I can wipe it and make it available again for the next thing that needs to be written. But again, this isn't stuff that I assume most folks here are not writing or like working on. Yeah, this stuff gets abstracted away at like a very high level, but I think it's important nonetheless.
Composed of 10 charge trap.
Cool. Wow. Thank you so much for all your time. I'm really, really, really grateful that you all showed up and you listened to my talk. Feel free to connect with me on LinkedIn. Also, we're hiring for several roles at Honor. We help seniors age at home with dignity and respect. So reach out if you'd like to learn more. Cool. Thank you.
Awesome. Thank you, Jake. Yes, applause all around.
Thanks, Jacob.
Thanks, everyone.
That was really cool. I didn't expect that you'd go from, carvings and a bone to SSD drives so quickly.
Yeah, Moore's Law. Things evolve pretty rapidly.
That's awesome. I'm sure there's some questions. Hopefully someone has. That was a lot of really fascinating information. So please, no question too ridiculous or silly. I have one myself that's probably ridiculous. But I want to open it up first to the audience. So you can unmute or just type it in chat if you want. If you can't talk.
My question is kind of like about the future of data storage. Like in 10 years, like what will we be talking about that's so different from what it is now? Like it's just going to be, I don't, yeah, I'm just curious, what do you think will happen in 10 years?
Yeah. So I'm not really sure how much smaller it can get than electrons.
Composed of 10
but
charge trap flash cells layered.
I'll show you. If you remember on this,
This is the basic unit of a computer's
I'll
long-term
show you
memory
one
storage,
second.
and it's called charge trap flash memory. 8 different levels for all the various amounts of electron charge.
Where I think it's headed is these cells will store more and more. Like we'll be able to differentiate a higher order of, a finer order of like electrons being stored. So it started with just the absence or presence of electrons, and then they were able to like differentiate, like this many electrons means 0, 0, 0, but this many electrons means 1, 0, 1. And so the more finely we can calculate the amount of electrons in a cell, the more data we can store there, and then the faster we can process that data. So that's where I think it's headed. But it's also, yeah.
Okay, cool.
Yeah,
I'm all for faster and better, so I'm excited for that then.
Yeah, it's pretty cool. I was just Googling, like, is there anything smaller than an electron? And I think it's a neutrino.
Okay. Yeah.
Is that where we're headed next?
Maybe. Yeah. I'm not a physicist, so I can't confidently speak to that.
We have another question in the chat. Based on what you were mentioning with how data is too small on the block level to override, does that mean data can't ever actually be fully erased? And if that's the case, is it possible to revisit what would be deleted data that's simply outdated?
Good question. So it can only be deleted at the block level. So what that means is like if a block is like 99% stale data, the computer will move the relevant data to a different block and then just wipe the whole, they'll just like send a crap ton of electricity through the block and then reset all of the cells within that block. So to your point, like to revisit what it means to be deleted, yeah, if that block has stale data in it and it hasn't gotten to the point where the computer has decided to like move it and clear it out, then yeah, that data actually isn't deleted yet. It's still captured on that block. And what'll happen is when you get a new computer, a new solid state drive, it'll just go through all the blocks it has available, which is like thousands of these. Like this video was at the like microscopic level or nanoscopic level. So when you get a new computer, it'll fill up all the blocks and then it'll go and then start reorganizing how things are stored.
That's a great question. That kind of brings me to, so my question, this was actually this kind of a half story too. You brought up my DJing and vinyl and, storing data. I was DJing way back when at a party and I had a music on a hard drive and it was an old school hard drive, like the platter, whatever. I didn't know how exactly it worked, but you mentioned magnets and stuff. Anyway, I was accessing music on the drive and someone knocked into the table, of course, everyone's drinking, and it fell off the table. So maybe you could explain like what exactly happened, but I lost some pictures or I really wanted on there, and I sent it away to a company to recover said data. What was happening and like why did that happen?
I think if I had to guess, I think what probably happened was the data, like maybe there was something blocking how the magnets could get processed by the spindle. Because if the data was still there, that means that the magnets didn't get reset. There must have just been something blocking how the magnets got like red. So either maybe they cleaned the platter, maybe they used a different type of spindle that can like pierce through jungle juice or whatever was spilled onto the platter.
Well, I think it was almost the action of just the fact that it was being accessed while it fell. Because with SSDs, that is no problem, right? Like with SSDs, you could like throw the disk around and it's fine, right? I mean, I wouldn't do that. I wouldn't recommend it, but
yeah. So like as this is being accessed, it's moving, and then if it like drops, I think it just like the fact that it's moving, like it's not in a secure place.
Yeah.
So that makes it more vulnerable to like also if it's accessing a different platter, it'll like maybe lift up the platter so that it.
Yeah, as Dylan said, magnets don't love impacts. Ask your fridge magnet that's hit the floor a few times.
Yeah, that's a good point. Magnets can just like lose their charge, which is to the point as to why like solid state drives were pretty revolutionary.
Well, yeah, I loved your excitement around SSDs because I think we all felt like that. We were like, holy crap, these things are so fast, right? And like your operating system, I remember it was like a party trick. You're like, I'm restarting, and you're back in like 5 seconds versus like 2 minutes. Maybe not a party trick, but yeah.
Don't know what kind of parties you went to.
yeah. I majored in computer science. Yeah. Any other questions from the audience? No? Awesome.
Cool.
Well, Jacob, you're an awesome presenter, and
Proposed to 10 charge trap.
You can teach, and those videos, that was pretty cool. So thank you everyone for your time. We'll send this recording out so you can watch it. I know someone else messaged me they had to leave, and so they want to see the rest. But yeah, awesome presentation, Jacob. Thank you, and thanks everybody.
Thanks,
everyone.
everyone.
We'll see you for the next one.
Thanks, Jacob.